Alright, so what the divergence theorem does is it gives us the relationship between a triple integral over a solid region Q and a surface integral over the surface of Q. Of course, the surface has to be closed. Can't be open. Has to be a solid surface. So if Q is a solid surface where we can evaluate a triple integral, and S is a closed surface that is oriented outward by normal unit vectors. So let me show you what I'm talking about. And this is in your ebook, but so you can see that the solid Q is the entire solid region, or the entire region, and it's closed. It's not like it's just the opening of a paraboloid. You know, we have a top there, a dome on top of the paraboloid, and we have normal unit vectors that can be found from each surface, of course, by taking cross products of tangent unit vectors or whatever. Then divergence theorem says that if Q is a solid region bounded by these closed surfaces and oriented by each surface is oriented by a unit normal vector directed outward from Q, then if F is a vector field whose component functions have continuous first partial derivatives in Q, the double integral over the surface of F dot N, that's the F is what? Vector field. N is the unit normal vectors, normal unit vectors, or how you want to say it. That will be equal to the triple integral over Q of the divergence of F, and it's not dA anymore, it's dV. That's the divergence theorem. Sometimes divergence theorem is referred to as Gauss's theorem. It's also sometimes called Stokes theorem after a Russian mathematician who lived in the 1800s, who lived to the crisp age of 60. So, do you remember the divergence of F? So let me write down, I can write down the proof of why this is what it is, and it'll give you that divergence of F in there. So the proof to show this just says that if we have this double integral over the surface, remember this is a line integral too, but it's also, this is double integral over the surface of F dotted with N ds, then that would be equal to the double integral over the surface of, well, then you'd have to do F dot N. So it would be M times I dotted with N plus N times J dotted with N plus P times K dotted with N. So whatever that normal unit vector is, ds, which then would be equal to the triple integral over the solid region Q of the partial derivative of M with respect to X plus the partial derivative of N with respect to Y plus the partial derivative of P with respect to Z dv. So that's if we have, I didn't write this down, we have the force xyz equals mi plus nj plus pk. Now, this end and this end are different. This end refers to whatever the component in front of j. This end refers to the normal unit vector. So like all of these, all of those, that's from the normal unit vector. And I keep saying normal unit vector, it's unit normal vector. Alright, even though the divergence theorem that we have here is stated for a simple solid region Q bounded by a closed surface, the theorem is also valid for regions that are the finite unions of simple solid regions. So like if you have a bunch of solid regions stuck together, if the big region is a bunch of smaller regions like this, so the entire region is made up of the union, it'd be like, it'd be S1 union with S2 union with S3. Of course, each one of these surfaces has to be defined as some function. You can see the way they have these two here. They have S1 is defined as G sub 2 of XY, or that's S2, S sub 2. And S sub 1 is defined as G, or Z equals G sub 1 of XY. The middle one here, I guess I didn't define it. It won't, it won't be going up or down. It's just horizontal. All right, so let's work a problem using the divergence theorem. So you don't have to copy all this down. You can just copy down the problem if you want to. So we're going to let Q be the solid region bounded by the coordinate plane and the plane here. We're going to let our force equal this, and we're going to find the double integral over the surface of F dotted with N ds. So let me show you what the figure would look like. So if it's bounded by the coordinate planes, that means it's bounded by the xy plane, the xz plane, and the yz plane. So that's why it looks like, and I'm probably going to make this a little smaller. That's why it looks like that. Alright, so it's bounded by these different planes, so that just traps it in the first octant. So what you would normally need to do here is you would need to evaluate 4 surface integrals to be able to figure this out using the knowledge that you may or may not have had before this class. However, by using the divergence theorem, we're able to make this problem a lot simpler. Instead of working out 4 surface integrals, because Q is bounded by 4 different surfaces. So you got, there's a surface, the xz plane, there's a surface, the yz plane, there's a surface, the xy plane, and there's a surface, and that was our equation. But instead of doing that, by using divergence theorem, we actually only have to find, because remember, what's the definition? The definition is the double integral over the surface of f dot n ds is equal to, it's going to be one integral, or one, I guess you could say one integral, but it's going to be one triple integral. We just need to find the divergence of f, and then we'll bound it. We'll do dx, dy, dz, dy, whatever's the easiest way to bound the thing. Okay, so the first thing you need to do is you need to find the divergence of f. Okay, so remember the divergence of f? That was back a couple sections ago. That's the partial derivative of m with respect to x plus the partial derivative of n with respect to y plus the partial derivative of p with respect to z. And we have our force field there. So it's just going to be, there's m, n, and p. So it's going to be 1 plus 2y plus 1. Sorry. So it's going to be 2 plus 2y. So that's what goes there in our triple integral. So we have 2 plus 2y. And now we need to do the dv. So dv is either, we have 6 different possible combinations. Let's set this up. dz, dx, dy. What was the function again? I'm just going to write the function again right here. 2x plus 2y plus z equals 6. Alright, so if we take this equation, and we're in the first octant, right? Because we were bounded by all those different planes. So if we take this equation and we solve it for z, then we'll get, so bottom is 0, Well, bottom is going to be 0 for everything because we're in the first octant. But this up here is going to be what then? If I solve for z in that equation, 6 minus 2x minus 2y. Okay. Now what do? Now I let z equal what? 0. I'm getting the, now I need to get the x boundaries. You know, my z is bound between 0 and this. My x is bound, well, I get rid of the z, and now solve for x, and you'll have the boundaries for x. So we have 2x equals 6 minus 2y, or if you divide by 2, you get what? 3 minus y, like a boss. All right, and then to set the boundaries for the y, remember we want to get just a number, all right? We just on this last one here. So we let the z equal 0 and we let the x equal 0. So then I would have 2y equals 6. So our last one's going to be 0 to what? 3. All right. So you can see neither one of these terms have a z in it, but when you integrate with respect to z, that's going to give you 2z plus 2yz. So you just need to evaluate that here. When you evaluate that, you're going to end up getting, just to save time, you're going to get 12 minus 4x plus 8y minus 4xy minus 4y squared. That's what you get if you plug it in for z there and there and multiply it out and put your terms together. So we're left with a double integral from 0 to 3, 0 to 3 minus y of all of that dx dy. All right, so now we integrate with respect to x. So that's going to be 12x minus 2x squared plus 8xy minus 2x squared y minus 4xy squared, evaluated from 0 to 3 minus y. We still have our dy left. Just to save time, what would we plug in the 3 minus y in for? Every x value. So that is going to take a little algebra time to do. But to save time, I'll tell you what that's going to be. Once you plug all that in, and then you plug in a 0, which it will give you all zeros, you're going to end up with 18 plus 6y minus 10y squared plus 2y cubed dy. Alright, so that's what you get if you just plug it in and then algebra it, and you get that. So now, here's the last part. We integrate now with respect to y. We have 18y plus it's going to be 3y squared minus 10y cubed over 3 plus 1/2, yeah. So that's going to be y to the 4th over 2, evaluated from 0 to 3. Of course, you got a y everywhere, so the 0 gives you 0. That's great. Plug in the 3 and put all those fractions together, and you get 63 over 2. Again, I told you this could be used to calculate flux. Just going to show you, I guess you could say, a real-world example. All right, so if we have this region bounded by, let Q be a region, you don't have to write this down, bounded by the sphere, find the outward flux of the vector field. Here's the vector field through the sphere. You know, the vector field can be a magnetic field, it can be whatever, gravitational field. So by divergence theorem, the flux across S would equal to this, and then we have our equation. Once we take all of our, we do the divergence, we end up with this. And it says using spherical coordinates is the easiest way to evaluate this. And so what they did is they went back and they plugged in all of those, you know, the dV is not dy dx or dz dy dx or dy dz dx dy. It's equal to rho squared sine phi, you know, and then all of this here. So you set up, you plug in, then you set up your different, your d theta. You got to bound your theta, bound your phi, and bound your rho. And your rho, remember, is your radius. So then you would have this triple integral here, and that would be the amount of flux flowing through that sphere if you had that that particular force field. All right. So moving along to the last topic that is usually taught in every Calculus 4 class, that is, I guess you could say, worth its weight in gold, is Stokes Theorem. It's just something that was not taught at Colin and lots of community colleges until a few semesters ago, when universities said, hey, we teach all the way through Stokes Theorem. Why don't y'all? You know, they have that love-hate relationship, right? We love them and they hate us. So we just decided they told us we need to be teaching it, so now we're going to teach it. We're going to use Stokes Theorem, and then it involves the curl. If you remember, we went over the curl in, you know, like 15.1 or something. But you can use the curl to analyze the motion of rotating liquid. So those of you that have the opportunity to take fluid dynamics, you'll be probably using Stokes Theorem whether you want to or not. All right, so for Stokes Theorem, we still got to have that closed space. You got to have some type of surface, and you know, the closed space is a projection mapped from some region to that space. So let me show you this picture before we write down Stokes Theorem, because it's kind of hard for you to picture this since, you know, you haven't been teaching calculus 15 years, and I haven't been teaching this but about 3. So so you can see it's closed. You can see it has a unit normal vector, and we have the projection down here in the XY plane. It is that counterclockwise rotation over some region. It's smooth. It's not broken into pieces. The positive direction along C is counterclockwise relative to this normal vector, you see. Counterclockwise, counterclockwise, counterclockwise. I bet some of you have seen something like this in physics. I know that I did, and it made about as much sense then as it does to me now, because I'm not a physics person. It's funny to me that they use this picture here. Right hand rule, you know. So it's probably one of the first things you learn whenever you start talking about vectors. Yeah, because you're sitting there working a problem and you're like, what are you doing? You giving me a thumbs down there? Like y'all do on all my YouTube videos, you always give me thumbs down. Oh, you gave me a subscriber and a thumbs up. I even had one person in here tell me the video's going viral. So they may get lots of bonus points. Yeah, that was you. I like giving out bonus points. I'm pretty much the bonus point king. That's my YouTube name. That's gonna be my Apex handle. All right, so we've already written this down once. This is just an alternate form of, again, Green's theorem. So the only difference really is that we have to take the curl. Note that the line integral here, this line integral, you could write that like this. Or you could write it like this. We went over all of these when we went over Green's theorem. So, but this is Stokes theorem right here. This is that special. That's Stokes theorem. But you do have to remember how to take the curl to be able to do Stokes theorem. That was another one of those things we went over, I think, in the first section. So let's do this problem. I think we're using the same function that we used with the divergence theorem. Looks like we have a different force field though, or vector field. I don't know why they spaced it out so much. So we got 2x plus 2y plus z equals 6. You know, you've actually already seen this picture, but you know, we were bound, I guess, particularly about the same way. We're bound here. All right. How do you get that x plus y equals 3 down there? You know, we have these different paths now. You know, it's closed here. Well, they let z equal 0. If z equals 0, x plus y equals 3. All right. I mean, this is partially cut off up here, but what number is this? It's 6. I mean, that's what our surface is equal to. So the first thing we have to do is find the curl of f. So what's the curl of f? Remember? I, j, k, partial derivative. I think I actually just gave you the formula so you don't have to do this right here. But if you look back in your notes, you'll see the formula. And then you have to put down your x component, your y component, and your z component. And then I'm not going to go through and evaluate that all the way because I gave you the formula. You end up getting negative I minus j plus 2yk. All right. So here our z is going to be equal to g of xy, which is going to be equal to 6 minus 2x minus 2y. All right, so this double integral, the curl of f dotted with n ds is equal to the double integral over the region of negative I minus j plus 2yk dotted with negative g, the first partial derivative of g, the negative of the first partial derivative of g times I minus the first partial derivative of g with respect to y times j plus k dA. All right, that all of this, that's the upward normal vector. All right, so what that ends up being, whenever you calculate that from z, so we have negative I minus j plus 2yk. You calculate that from, again, z here, and you get, it's going to be dotted with 2i plus 2j plus k dA, or the double integral over the region of, do the dot product, and what do you get? I, j, and plus 2yk. So it's just one, wait, no, it's 2 plus 2 plus 2y, or not, negative 2, sorry. Man, my math is off. I'm doing dot product. Negative 2, and positive 2y. So that's 2y minus 4. And if it's dA, let's just set it up dx dy. So we use our equation. That was that same equation, remember, that 6 minus 2x minus 2y, set z equal to 0. The x's will be bound between 0 and 3 minus y. The y's will be bound between 0 and 3. And I'm not going to go through all that, but you would get negative 9. So that is the value of the line integral by using Stokes Theorem. So you could go back and do it the long way like we did with the parametricization. So let's say we didn't have, and I know it's just about time, well, it's over time to go. But if we didn't have Stokes Theorem and we had to use the parametricization, and you don't have to write this down, I just want to show it to you. For that figure that we had, you could set your parametricization up like that for each one of those paths. But then that would mean that we got to do 3 integrals to find the sum of all of that. And so if we did all of that work using that original line integral formula, we would get the same answer, but you could see it'd be a whole lot more work to do. Okay, so Stokes theorem simply makes it easier to evaluate that line integral.